Hello everyone and welcome to this new episode of Power Up. Today we will talk how to reduce the energy consumed by household appliances. Power electronics, as you know, must improve efficiency to meet international standards and reduce power waste, making in this way products more sustainable. From mobile phone chargers to industrial SMPS, all AC-powered applications need power supplies. The load receives all AC mains power in an ideal power supply. This only works if the current and voltage are in phase. The grid loses energy if current and voltage are out of phase. A power supply's power factor correction (PFC) stage tries to achieve the best power factor. Cambridge startup Pulsiv emerged with their power electronics technology. Pulsiv technology transforms AC to DC without a PFC inductor by charging and discharging a small storage capacitor. According to Pulsiv, this solution has a high power factor, continuous efficiency, and compact system architecture. It may reduce costs and reduce global energy use. In this podcast with Darrell Kingham, Chief Executive Officer of Pulsiv, we will analyze how Pulsiv is reaching this market goal with a patent solution. Darrell brings a strong engineering background, many years of experience leading commercial organizations, and a track record of delivering long-term growth. Previously head of ARM's European sales operation, he is working with industry to deploy Pulsiv technology where it can deliver the most value. Let's talk with Darrell. Hi Darrell, thanks a lot for being here at Power Up. How are you?
Good afternoon, Maurizio. Yeah, really good to speak to you again. Thank you.
Thank you. So where are you located, Darrell?
So our head office is based in Cambridge, and I'm a short distance from there. So I've been in that area for quite some time.
Good. So we will talk about a lot today, power electronics technology. But before going through my questions, tell power electronics community more about you, your background.
So I've got a degree in electronics engineering. So I started off life as a design engineer way back in that was 30 years ago now. But I realized pretty quickly that I preferred the commercial world. So I moved into semiconductors. I was an FAE at the beginning, and then product management, and moved up through the chain. And then I got headhunted into ARM to be one of their sales guys. And I was at ARM for many years and had various roles at ARM, and that's a fantastic company, great place to work. I learned so much there. And then when I got to my end of the time at ARM, I was really looking for something interesting to do, and I tried a few things, and then I ended up having a conversation with Pulsiv when they wanted to kick the whole thing off. And I really got on with Zaki. I really believed in what he was trying to do. And secondly, I just saw the opportunity. So I jumped into this, and I've been doing it now for a couple of years, and it's been a great journey so far.
As I said earlier, Pulsiv technology would transform AC to DC without a PFC inductor by charging and discharging a small storage capacitor. So we would like to understand more about this solution. Your solution is an alternative approach, where we can control the charge, the discharge, and so on. So can you describe the process?
When I first spoke to Zaki, I think that the main thing he wanted to do was to find a way of making sure that any electrical product that we plug into the wall is getting the most out of the electricity that's consuming and not waste it. Now, in an ideal world, the power electronics in any product, you don't want it to waste any energy, right? You want all of that energy to end up running your TV or playing your music or entertaining you in some way or mowing your lawn, whatever it is that it's doing. And what we discovered was that, if you in power supplies that are designed for, any power level above 60 watts, where they need power factor correction, there was quite a lot of energy being wasted just by virtue of the way it's traditionally been done. So what Zaki figured out was a new way of doing it. And what he really uncovered was the fact that in a typical design, you have a series inductor that all of the energy that your product consumes goes through, regardless of whether it's in standby mode, whether it's running at full power. And obviously, as soon as you've got anything in series, it's going to cause losses in your system. And Zaki said, well, could I come up with a way of removing that component entirely and doing it a different way? So with our solution, that's what we've done. And it's a completely new way of doing AC to DC conversion. So we can deliver efficiency and high power factor with a single platform and scale from, well, at the moment we're going up to 250 watts, but we've got another design coming that will take us up to 600, and we don't know how far we can push it yet. But we started at the low end just because that's where all the volume is, and that's where obviously, you know, we can address the largest number of devices where this problem exists.
So you mentioned Zach, that is your colleague, your engineering.
Yes, Zach is the inventor. Yeah, he's now the guy that's really running all the engineering and coming up with all the products.
So in terms of applications, so you mentioned just to avoid waste power. So I guess that you are doing marketing commercials just to spread the voice about your technology. What type of power electronics application is particularly suited for your solution?
Interestingly, I mean, you can argue that it's anything that's powered or charged from a main supply. Mm-hmm. But what we found is it's really highly relevant where you've got a variable load. Mm-hmm. If you've got something that runs all the time, then there are solutions out there that are efficient at peak performance, and they work very well there. But unfortunately, because of what I mentioned before about all of the power going through the series inductor, what that means is that if you're running things for a lot of the time in standby mode or in low power mode, so think about things like TVs that sit there for most of the time doing nothing, and it's only when they're powered up that you really care about high efficiency, high performance. Where you've got those things that are either being turned on or off during the day at different times, or that are operating at different loads, things like data centers is another one that we've thought about, or lighting, particularly dimmable lighting. Where you've got a variable load, that's where we bring the biggest advantage, although there are other reasons why you might use this where you've got something that's running constantly at a full power load as well. So
your approach is an alternative approach, so has extended the range of efficient designs, efficient flyback design in particular, where you reducing losses and improving overall energy consumption, as you said. What about how much is important? What about thermal management in this case and scalability for your application? How does the compact system architecture benefit end users in terms of design integration? Because here it's important just to reduce the form factor and to guarantee a small device at the end, like power supplies for consumers.
Yeah. So what you typically find is once you get above about 60 watts, mm-hmm. people have traditionally gone from flyback type. I mean, there are lots of power supply topologies, but flyback is a very popular one. They'll move to an LLC type topology, and with that comes additional cost, additional complexity. I know a lot of people would prefer not to use them if they didn't have to. So one of the things about pulsive osmium technology is that we've taken a single switch flyback up to 180 watts. So what it means is where you previously would have had to have used an LLC, you can now use a flyback instead. And that obviously opens up opportunities in all sorts of applications to now use lower cost solutions where you would otherwise have to use an LLC. So, I mean, think about things like laptop power supplies, mid-range TVs, LED lighting, games consoles, all those sorts of products. People can look at using Pulsiv plus a flyback as an alternative to boost PFC and an LLC solution. And that's where we're getting the most attention. I mean, there are other applications where there are specific reasons they use us, and it's nothing to do with using a flyback particularly, which we'll talk about later. But we're finding a huge demand now because, let's face it, people want efficient products, but they also don't want to pay a premium for them. So are there similar solutions of your technology? Or, I mean, if there are, what are the key advantages compared to traditional power electronics solutions? You mentioned efficiency for sure, but so your technology is just the only one. probably the key thing is the flat efficiency profile.
Mm-hmm.
What you don't want is that when it's running in low power, it's now burning proportionally more energy, which is what tends to happen today. If you look at on the Pulsiv website, you'll see that we've got lots of data on there about the fact that whether you're in standby or at full power, you get the same efficiency all the way across. But I think in addition to that, it's not just about efficiency. It's also the fact that you can eliminate things like inrush current. Now, I don't know if everyone is familiar with inrush current, but the idea that when you first switch something on, in order to get to a steady state position, there's a massive spike of energy that goes into a power supply typically, and it can be 40 to 80 times steady state, and that has all sorts of implications on your infrastructure. It can flick out breakers, it can damage wiring if you've got lots of them connected at the same time. And we're quite fortunate that with this technology, we eliminate inrush entirely. Now, people have said we don't believe you, but it's a fact.
You can eliminate inrush current, saving space and component cost. So how does Pulsiv technology compare to other methods of limiting inrush current?
There are methods of managing inrush current. Mm-hmm. So, one is you add additional components into your system, which obviously adds cost and complexity. There are power supplies that don't manage inrush current, and then you have to work around them by wiring them up onto different circuits or putting special breakers in when you're installing them. But all of those involve money. All of those involve doing something that you could avoid. So by using Pulsiv as standard in any kind of power supply, the problem of inrush just goes away. So all those things you've had to do before, you can just stop doing. You can just stop spending the money and stop adding the complexity. I mean, we think particularly in things like LED lighting, where you've got hundreds of LED lights potentially in a building, and you have to think about this really carefully. That's probably one of the biggest areas we see this as being an advantage.
Get it. So I have other two questions. One is if there are any future developments, improvements in your pipeline, in the pipeline of Pulsiv technology, maybe challenges and the next goal from your point of view.
Yeah, so the first product that we have is really designed for power supplies up to 250 watts. And we put a couple of reference designs out at the moment, which are really aimed at enabling companies to achieve all of the latest regulatory standards around efficiency, the Energy Star and the CEC, etc., and achieve that with the lowest cost. Okay. So there are people that just say, look, I don't care about the best efficiency. What I care about is spending the minimum amount of money to pass all those regulations. And that's what we started with. But one of the big questions that comes to us is, well, how far could you push the efficiency if we started to use things like GaN technology or silicon carbide and other components?
Sorry, indeed, my next question is a comment about the wide band gap.
Okay, yeah. So, I mean, the nice thing about the Pulsiv is, we're not tied to any particular technology. I mean, you can use any flyback technology, forward converters, quasi-resonant converters, whatever you want on the second stage. But what we haven't done yet is to see just how far we can push the performance. Because we've got a flat efficiency profile, which is fantastic, we wanted to get that line just above the standards at the lowest cost point. The next question is, well, how far could we push that line up with all of the premium solutions that are out there? And then we can give customers the choice between the absolute highest performance and the lowest cost. Okay, so the next thing we're going to do is to see, we're working with a number of companies at the moment to see if we can push that flat efficiency curve as high to 100% as we can, right? And that's one of the next things we're doing. Now, we know that some companies are already doing this themselves, but we want to be able to put reference designs out that anyone can use. So whilst there'll be a number of organizations that will do it their own way and they want to keep that to themselves, we want to put designs out there that is, freely available on the website for anyone to use. So that's one thing we're doing. The second thing we're doing is, the current solution is really tailored below 250 watts. We want to come up with a solution that pushes from 250 up to, we're initially targeting 600 watts, but we think it will go into the kilowatts for things like EV charging. That's also on the roadmap. And then some reference designs around those as well. So that's really our focus right now around the osmium technology.
This is a great plan. Good. Okay.
Thank you.
Okay, Darrell. Thanks a lot for joining us at Power Up.
Appreciate your time. All the best.